So our next speaker is Juho Kono. I wanted to give you a little bit background about Juho. Juho comes from Wärtsilä Corporation. He's responsible for the digital design platform development in the engines technology department based out of Finland. Since joining Wärtsilä in 2011, he has been working on structural analysis of four-stroke engines, and he has led several R&D projects. He holds a Master of Science degree from Helsinki University and a Doctor of Science degree from Aalto University. And the most interesting aspect of his bio is that he spends all of his free time working on precision agricultural practices on his nearby cereals farm. I would love to hear about that. All right. With that, please welcome Juho Kono.
Okay, thank you, Sumant, for the kind introduction, and thank you, Dassault and Simulia for hosting this great event and for inviting me to give a bit of insight what we've been doing with the platform. So we're talking about securing product performance, and what do we actually mean with that? It's all about meeting the targets with the product design. And doing that with the minimum amount of going back and reiterating. And we're going to see how we're using the 3DEXPERIENCE platform to leverage that. So we're going to be looking first a bit into our company, because I don't think the four-stroke medium-speed diesel is such a mass product that you're overly familiar with. And then take a look at a bit into what we actually simulate as a background, so you see with what kind of simulations we're working with. Then the core of this talk will be more on the requirements-based validation concept. What do we mean with that, coupled with the data-centered approach and going into simulation democratization and showing how the 3DEXPERIENCE platform helps us in that. But first, a bit about our company. So we're roughly 18,000 people, 70 countries, a technology company. We're of course known for the four-stroke engines, but our business nowadays is divided into marine, energy solutions, and then services. On the marine side, we're of course known as an engine manufacturer, but we're actually providing the whole deal for the ship, so everything from thrusters, propellers, gearboxes, all the way to the bridge engines. You can even buy toilet seats for your ship from us. And then the other part of it's of course the power plant side, or energy solutions as we call it nowadays. It used to be a lot about generating power somewhere where you didn't have anything else available. But now it's transforming a lot more into the smart power generation, meaning providing flexible power for balancing grids, for example, with the wind power coming more and more heavily into play. And the third cornerstone of our operation is the service business. So we service not only our own products, but quite a lot of other engines, for example, and we have a really wide service network. And that's in brief. I hope that gives some kind of quick overview who we are, where we come from. Then going a bit into the topic of the day and more into simulations. So where we started, so back in the 70s, it was pen and paper, but already in 73 we did the first finite element analysis. In 1980 we got the first personal computers, and then moving on into the 90s, we went more into hydrodynamic bearing analysis to begin with. Then we started And here's actually a connecting rod from '92, so there's happened quite a bit on the model accuracy since those times. Then going on to CFD, we do quite a bit of combustion CFD, for example, and of course the combustion is at the heart of the four-stroke engine, so that's really an important topic for us. Going into the 2000s, we started looking more and more at the whole engine. And during the 2000s, we've been really rapidly developing both the simulation methodologies, but also how we apply them, going more into DOEs, optimizations, looking at large data sets, but then also making the simulation methodology itself better. Multi-body methodologies, advancing finite element models, CFD. And what enables us is to do this is, of course, the massive increase in computational power. So we've been steadily investing in hardware. So with a roughly constant yearly investment, you get an exponential growth. So in 20 years, it's almost a factor of 1,000,000 that we've gone up in computational power. Then, of course, the software cost starts to dominate, and that's kind of like the resource nowadays, I think, from the cost point of view, because you want to really make sure that you utilize your software to the maximum. Going a bit more into the actual simulations, we're talking a lot about first time right. And that's really connected to how and why we run the simulations. And why do we need first time right? I think the answer is actually in this picture. It's the sheer scale of the products that we're making. First of all, it's of course the component cost. Big components cost a lot of money, take a lot of time to make. So prototyping, it's really expensive. And the other aspect is, of course, the testing. If you go more into testing-based validation, if you have that nice V8 engine in your car, you press the pedal, there's a small whirlpool going in the tank. Then if you're talking about something like 40, 50, 100 liters displacement per cylinder, the fuel cost is really substantial for the physical testing. So that's been a natural motivation always for us, why we want to promote the virtual testing more and more. Then some practical examples how we do things, and this is to highlight that we're going more and more into this kind of multi-physics setting. For example, for the cylinder head, we typically start from a combustion CFD. We go to a conjugate heat transfer for the cooling. Then from that, we take the thermal results. We're using Abacus here for the finite elements. We're using pretty complicated material models. We're also including more and more manufacturing effects, such as the casting effects, what the material actually is in the casting due to the cooling and so forth. Then another cornerstone of our modeling approach is the so-called virtual engine, which basically means multi-body models of the whole engine. So we try to make the multi-body model as complete as possible and to utilize that as much as possible. So it's not only for the vibrations, but you get a multitude of results out. You get oil films, you get loads for other simulations. And as an example of that workflow, for example, from the multi-body model, we're analyzing, of course, for example, the bearing results. We're taking those loads, transferring those to an Abacus model. Once again, here we're having casting effects included, a lot of contacts. And because you have big components, the simulations tend to be heavy. And having said that, big components doesn't mean that you're always looking everything on the micro scale. I wanted to show this example of the fretting phenomenon, which is it's really commonplace wherever you have frictional joints. So here basically the connecting rod is deforming from the bottom and you get a sliding between the shell and the housing. And then with innocent-looking stresses, you can get pretty nasty-looking results. And this has led us actually looking into micromechanics. And it's been really nice to see the amount of interest here going towards the multi-scale concept. And we're using here, for example, Abacus for modeling asperity phenomena and trying to go from those microscale or mesoscale results into something that we can utilize in the analysis workflow. And taking that bit further, we are now also modeling the metal itself on a grain level to try to understand what happens in the contact, and then try to take those to the simulations that we're actually running. And from our perspective, we're not trying to reinvent the wheel on the micro level, but our focus has been more on how do we take all of that good stuff that's been done in the micro modeling, and how do we make that into something that we can actually utilize. So that's a bit of a background for the talk actually, and to give an idea what kind of things are happening in the background. But then going more into the requirements-based validation concept. And I have an example from the 1600s to show that this is not a new thing. And of course, as a Finn, you want to take the Swedish engineering disaster as an example. But this is the Vasa boat. So what happened is that they sailed less than a mile from the harbor and basically tipped the whole boat over. And what was the reason for that becomes evident from this cross-section. They were going to war, and the other guy had more guns on their ship. So the king tells you, add another gun deck. What do you say? You say yes. And they added the other gun deck. The ship became top-heavy. The rest is history. But this is happening over and over and over and over again 400 years later, I would say. So this is why we're so concerned about the requirements, because they are actually the thing that guides us into the general direction that what are we trying to do. And that is why I think it's really important that they should be always visible and accessible to everyone involved in the design process. And the other aspect is that there's a lot of different levels of requirements. You might go from a really high level requirement, let's say the customer wants good fuel economy, into something really specific, something like a deformation on a certain component. But the important part is that they are never standalone. So there's always a link. And how can we use the 3D experience in this kind of case? This is a really typical engineering problem. So we have a too low safety factor in the cylinder head design. And then you start drilling down, why is that? And with the connected requirements, we're seeing that, okay, safety factor, temperature, they are linked. We see from the same requirement specification holding the validation results that, okay, let's go check out the temperatures. You have defined the limits for the temperatures, and then you recognize that, okay, it's actually a temperature problem. But where did that come from? You go yet another step back, you remember that, okay, there's of course the performance simulation that's giving us the boundary conditions for the cooling. And then you see that, okay, it's a problem with the performance requirement, that this is giving a too high heat load on the component. But that in itself is not the answer, because then you need to go yet another step. And in the end, someone defined why you're running that performance simulation at that specific load point, and through that you're actually then ending up with the customer requirement that he wanted, let's say, a specific fuel consumption at a specific ambient condition point. So from a very technical, detailed requirement, like the safety factor, in a couple of steps you're tracking back actually to something that was defined on a really high level customer requirement. And this is why we want to link them, to have that link and see what was the actual root cause of the problem. Then we're talking about linking the data and the results. So basically the answers to the validation question, is it okay or not? And why is it important that it's linked? So if we go back to that fuel consumption example, it's one innocent looking customer requirement. Then you get two product level requirements out of that. Let's say you want this fuel oil consumption at this point and this at the other ambient condition, for example. Still pretty manageable. But then when you start putting that to the component level, all of a sudden it's a handful of components. Each one has a dozen requirements that are, or half a dozen requirements that are somehow connected. And those requirements are connected to a set of parameters. So in this case, you might have actually 100 parameters that you're having to update to really see if that customer requirement is feasible. And to this end, this is where the platform really comes in. Because now we're having the requirements, the correlated parameters, and the simulations in the same platform. And we're using the test cases basically to define how are we going to show that this requirement is okay. So it states that we say that the temperatures are okay means that they are below the limit in this and this and this area. And this is the work that we do up front. And now, since we have also the simulation itself in the platform, we are connecting those directly to the same test cases and connecting that simulation also to the test case parameters. And through that process, we're doing it once for one product development. So now that we came up with the next iteration, so we have the next cylinder head design, for example. When you instantiate from the template that's pre-connected to your parameters, this can be the analyst guy, this can be the designer, whoever is the component responsible. He runs the simulation, and when he's done, his results will be directly connected to the requirement specification. So we want to use the requirements tool as a snapshot into the current validation status, but not only as a status indicator so that you have a green or red box, but we actually want to bring in the latest data from each and every simulation run. So now when he hits update on this sort of master view on the validation, his parameter values will be updated by that simulation process. So we're providing that guy who is interested in the validation results an always up-to-date view into the status, into the few key results. So for example, he's then seeing directly from that simulation run what happened to my cylinder head, what happened to my liner. Then the other part related to these requirements is project planning. And planning, as we know, it's sometimes not the favorite topic, because it's of course a lot of hard work. And how can we alleviate that amount of work is by using this in a similar way. So our idea for the simulation project planning is that you should start by defining what are you going to do, by defining your requirements. Then you set the how with the test cases, and then the actual work is the simulation tasks that you will end up with. In traditional project planning, you start quite often from the work. So we need to do this bit of work, then you put it into a schedule. But I think that in simulation-based project planning, if we want to call it that, we should just simply flip it over. So start from the end. And this is what's actually demonstrated here. So let's say we have a new engine development project. And we start figuring out what to do. We know that we need to run run some kind of analysis once again on the head. So you're starting with the project planning. But now you're starting from the end. So you're not starting with that item that, okay, I need to build the model, I need to prepare the CAD. But we're starting by saying that, okay, in the end, we have to do some design iterations. But why we're putting that item there is that we are now using the platform once again to use those requirements that we have already existing in that same place. So we start from that task that is going to be the one that delivers your targets. And to that one, we're now linking, for example, the requirements. So these requirements are actually the only thing why you are doing this specific validation task. You're doing it because you want to fulfill the temperature targets. The next step in this one is going then backtracking the track. How are you going to get there? So then you figure out that, okay, typically we need to run 10, 15, 20 designs. So it makes probably sense to create some kind of simulation template, for example, in this case. And we define that as a task. In the same way, we link those tasks, so you need to get the template done before you can start on your design iterations. But once again, since we have the project planning and the actual simulation work in the same place, we can connect as a target or deliverable into this simulation task, the actual simulation work which is preparing the template. And when we create the project plan in this way, we're actually forced to combine all the disciplines. You're forced to combine the design guys, you're forced to combine the analysis guys, whoever is involved, and the plan starts growing naturally. And then, of course, we want to reuse this. So our vision with this is that we're not doing project planning for the sake of planning, and then planning separately how we're going to do the simulation, because that you need to do in any case. So we just want to reutilize that thinking work that we do on how we're actually going to perform the simulation and use that as basis for the project planning. Okay, moving on a bit. There's been a lot of talk on data today already. And we're on the same bandwagon, so to say, with this data-centered approach. And this is sort of the motivation. I've spent quite a few moments of my life checking various simulation reports. And this isn't even the longest one, but typically this is 100 slides roughly. And I counted that 13 slides of those, we're basically copy-pasting input data. So something that you have in the model, you're just re-reporting it to be safe. This is, of course, something that the platform immediately takes care of. Then we're repeating some previously reported results. And then we have this myriad of semi-automatically generated slides. More or less readable. But this is the sad truth that typically 99% of the people only check the conclusions, or the next slide with a couple of colorful pictures. And what's in the conclusions? Typically, you're comparing, let's say, 5 numbers against 5 numbers. And it's exactly those 5 numbers that we're now putting into the requirements management tool to be visible there. But what do we do when we really need to dig down deep into the results? So from the key figures, you get the rough and right idea, you see where we're going. But sometimes you really need to go and really dig out the models, see what it looks like. And we're not trying to get rid of reporting, but to change the way that we report results. And to that end, we're really trying to heavily use these dashboards as a means of reporting interactively, providing access to the data. Like we saw a similar thing in Andy's presentation, the key is that you can provide the data to a lot of people, and you also provide the opportunity to communicate or save your communication. So for example, annotate the designs, say that this is good because of that. Maybe you should be looking into this. And then instead of compressing, let's say, 1 terabyte of 3D data into 100 pixels, you should be really giving the access to that whole 3D data through the platform. And I think one key aspect in this is as well that it all runs in the web browser. So it's really easy for the casual user to come in, start using, and get the access to the data that he needs more or less immediately. So to recap in short the whole requirements-based validation concept that we have going on, one of the important key features is this sort of key figures connected parameters idea, that we're giving the most important 5 numbers, clearly visible, always connected, always the latest data. Then we can track the validation process smartly by using the test cases, so you're seeing always the up-to-date view of where we're going, what's okay, what's not. And then using the dashboards and the fact that you have the data in the platform so that you can also provide any user a suitable view into that data. And this is then leading also into simulation democratization, and this is something that's been a hot topic for quite a few years now, and I think it's picking up more and more. And why it is so important? So this is a typical case, and even the measurements are actual, because I happen to remember this case very well. The timing might not be. But let's say you're designing something like a connecting rod. And then the guy responsible, we call them engine experts, so he comes up with an idea. What would it look like if we increase the diameter or decrease the diameter by 1 millimeter? So status quo, what he would do, send an email to the simulation manager. And then where the email is, it's typically sitting in the inbox. And I took the optimistic average of 3 days into this one. So he figures out that, okay, there's this guy, he's ready to do the work. It's in his inbox for yet another 3 days. Then he gets started. He has the model, maybe automated, so he changes the parameter, takes something like 15 minutes. He spends 3 hours running the simulation. Then maybe the post-processing takes like a day. He has to produce pictures. He doesn't remember what script he used the last time, etc. He has it done. He emails it back to the manager. 3 days in the inbox, minimum. Someone's checking it. At least 1 day. Then it's sitting in that guy's inbox who requested it, because he is already frustrated. He decided to go with the original 190 millimeters in any case. These simulation guys never get anything done. But why is that? Because the simulation took 3 hours and 15 minutes, but we were emailing back and forth something like 14 working days. And this is the thing that we try to solve with the democratization. This is not the connecting rod template, this is something different, but to give you the idea how it then happens in practice. So we're doing something simple here, an IX calculation for those of you who know engines. It's sort of semi-analytical, a bit of finite element method analysis for the crankshaft. one of those things that if you're a simulation guy, you couldn't care less, but you just have to do it. It's not fun by any means. It just needs to get done. But now, instead of that email loop, we're providing the template, providing to the guy who really needs the results access to those parameters that are relevant to him. He can click, and then when he's clicking, he's figuring out that, okay, maybe I'll run a few other cases while I'm at it. And creates those simulation processes. Everything's happening in the web browser. A couple of minutes, he's done, and he's running the simulations. But that only got us halfway through. So basically we went from, let's say, 7 working days into more or less immediate. So now we're running. But what's he gonna do when the result's complete? And I think this is an equally important part of the democratization. Providing the models to run, making them easy to run, that's one part. But then you need to provide the results as something usable, something that makes sense. And for that purpose, I think the result analytics is really a good tool in this aspect. And in this one, we're looking at the cylinder head process. It's a concept process, and we'd be running that by someone else, preferably not the simulation guy. First step, how it's connected to the platform, is like we saw previously, that you can use the requirements directly. So we're setting the limit, for example, for the flame deck temperature from your requirement specification. So you know that when you're looking at the results, your limits are the correct ones. They are the ones that are agreed in your organization. You're not typing them. You're not selecting them by yourself. So you have the traceability going back to the requirements. Okay, now it looks like we were a bit too harsh on the temperature. We were left with only one design choice. But this is the second step, that you really give the interactivity to that user who needs to access the data. You're not going to be emailing back and forth the different options or updating some Excel. He can directly go and click, okay, maybe I was a bit too harsh on the temperature boundary conditions. I'm going to look at the infeasible designs as well. Then he knows that these start looking pretty good, but I want to narrow it down a bit, maybe take the lowest safety factors away, and then move forward. And everything is happening in the browser. And one important thing is that the workflow is exactly the same each and every time he's using it. So he knows that whatever data he has, he always has the same workflow at his disposal. Okay, then of course you can get this far with Excel or something like that. But what really is the key here is that you can bring all kinds of content. Whenever you're doing this parameter against the other, you find something that doesn't quite add up. You see that there's something going on here. But now with the platform, you don't have to go find those reports, start comparing them side by side. But in the same way as with the dashboards, you have the immediate access to that data. It can be 3D like here, it can be pictures, charts, whatever. And you can really drill down directly, deep into the reasons that why does my parametric comparison look like this, understand, eliminate maybe some points that don't make sense. And the last but not least is the capability to actually save your decision making with the results. We've had a lot of let's say skeptic faces about this like button in the company, but I think that's something that you cannot fight anymore. So the social media is there to stay. But the whole idea in here is that you're actually bringing the interactivity and storing what you did, how you ended up there, and all the reasoning. You're saving that in one place together with the data. So no more minutes of meeting somewhere, simulation report here, some Excel here, some notes here. But you're really bringing it all together. Then when you need to go back 5 years later, figure out that what was wrong with the validation, you're knowing that you will find those results, the models, and most importantly, I think, actually the reasoning behind that, why we did it like we did, and hopefully learn from that for the next round. So then we solved also the right-hand side. And this is, I think, what my vision is to convey to the end user of whatever you're democratizing. That when he's done, he should have the sweet taste of honey in his mouth and be kind of waiting to do the next one. So that is really something that then drives it, I think. And when you get one in, then the next guy sitting next to him, he's thinking that, no, why can't you do something like that for us? And then it starts also naturally spreading. So you need to get kind of like a few of the good examples out. And I think that's helping the adoption quite a bit, that you take something that works, show it, get it out there, and then people start getting the ideas that, why can't I do this in my case? So, something to conclude. This is the scary slide, the conclusions. Did we learn something or not? Hopefully. So, we've been talking a lot about requirements, and they've been stressed in other presentations in this conference as well, and I think that is really important, because they are sort of the baseline into what we really should be doing. You need to set the targets. You need to say, this is when my concept is ready. This is when my detailed design is ready. And you need to do that up front. Related to that is of course the planning. You need to plan how to get there. And here also, I think the reuse is the key. First time around, it's a huge undertaking to really go and plan the simulation. But if you do it smartly, you connect it directly to the processes, you're actually sort of templatizing the whole simulation workflow on a task level, not only on the process level. And last but not least is the data. So the target in our implementation is always to be directly connected to the data. You remove the man in the loop in those cases where it's an extra effort, and by providing the access to the data, you put the human where he's at his best. So you give him the data, you give him the tools how to interact with the data and to support the decision making. And I think the lesson that we've learned at least is that the arrows between these three are the important part. And that is really what this kind of platform thinking is enabling. You have it by default in the same place, and you have it connected. So, like Forrest Gump said, that's all I have to say about the requirements-based validation thing. So, hopefully, I conveyed a bit our vision on this, and I would like to thank everyone for listening in, and thank you once again for Dassault Systems for hosting and having me here.